Hi, I am Alexi, and in this presentation I will be discussing some proofs regarding the XOR cipher. Before I start, I would like to discuss a bit about myself. I am an undergraduate student of computer science with a minor in mathematics and a concentration in data analysis. In my spare time, one of my hobbies is doing recreational maths and old school hacking. I'm also really bad at explaining things. I feel that I'm better at doing things than explaining them, but here I will prove a theorem with a formal methodology. So hopefully my ability to do maths will compensate for my impairment regarding my capacity to explain things. So let's get started. A bit of background. XOR ciphers are really important in today's world. They form the basis of modern encryption. Think the advanced encryption standard, the blowfish algorithm. And some people might think that the XOR cipher is magic, or maybe they just don't understand how it works. I hope to demonstrate that the XOR cipher is better looked at through a logical deduction lens than a supernaturalistic lens. And also keep in mind, I'm not that clever. I was made aware of this theorem from the textbook Computer Science and Interdisciplinary Approach, and the authors constructed a proof with binary algebra or Boolean algebra. And my contribution here is to build on what the authors of this textbook wrote regarding the theorem. So the claim here is that given a plain text message M, a key K, and an encrypted message C, the conjecture is that M is materially equivalent to itself that has gone through an XOR operation twice with the K, which in turn is materially equivalent to C that has been XOR'd by K. The implications of this theorem is that the XOR cipher will give the user consistent plain text after running itself twice with the key. There are two ways to prove this. The first is with a truth table, and the second is with binary algebraic manipulation. The authors of the computer science textbook discuss the algebraic method, but I'll start with the truth table method. A truth table is an exhaustion of all possible inputs for a given well-formulated logical formula and its results. An interesting piece of trivia: some logicians, such as the author of Logic for Dummies, believe that the XOR operator is redundant. The only needed operators are negation, conjunction, disjunction, implication, and material equivalence operation. I don't necessarily agree with this, but it's worth pointing out. And here we have the solutions for the truth table. Remember that I contended that M is materially equivalent to M itself XOR'd by the K twice, which in turn is materially equivalent to C XOR'd with K. And we can see that this is true because the M column, if we look at the M column, the M XOR'd with K twice column and the C XOR'd with K column, if you examine the rows, they are all equal to each other in all possible interpretations of what, no matter what C or K is. And material equivalence is defined as having these columns being equal. So this is one way to prove it. The other way to prove it is, again, at the risk of sounding repetitive, with the method described by the authors of the computer science textbook, with the binary algebra method. in mathematics, we start with a set of basic assumptions, postulates, and then from those basic definitions and postulates, we derive theorems. It's less computationally expensive than truth tables, and it's more, I guess you could say, a smarter or a more intuitive way to prove theorems. These are some of the rules of binary algebra. If you XOR a variable with 0, you get you start with the same variable. That's identity. Annihilation is when you XOR a variable by itself, you get 0. And associativity is XORing something. I don't know. Again, I'm bad at explaining things. I can't. I don't know how to explain associativity. But if you took a high school algebra class, it's a very similar concept. And we can prove that M XORed with K twice is identical to itself. By starting with the initial claim, we can apply the associativity principle, then annihilation, and then identity. I'm just narrating at this point, and final thoughts. So I'll just end with some food for thought. Nothing in computers is magic. Every operation that a computer performs can be explained with a mathematical methodology. And also, I think hackers should study a bit of theoretical computer science. Hackers, they like to tinker with technology and grow their knowledge their collective knowledge from tinkering. And I'm not saying that they shouldn't do that, but I feel that theoretical computer science can complement their skill set. Thank you for your time. I know this may have been a little bit awkward in my presentation, but I hope you learned something new. Goodbye.